And now I'm going to show you the calculation for the special case of a geometric offspring distribution in the Galton-Watson process. I want to assume now that the distribution for offsprings at each amoeba, is pessimistic, geometric, with some parameter p. Remember, pessimistic geometric is the number of failures before the first success. Okay? The expectation of the pessimistic geometric, expectation of the offspring distribution, is, I always remember the optimistic geometric, but then the pessimistic is one less. So the optimistic is the reciprocal of the success probability. This is one less. So it's going to be 1 minus p over p, or q over p, which is actually less than 1 if q is smaller than p, which is equivalent to p being bigger than 1/2. If there is a success with probability at least bigger than 1/2, then the average waiting time is less than 1. It is equal to 1 when q equals to p, so p equals to 1/2, and it is going to be bigger than 1 if q is larger than p, so the success probability is less than 1/2. If the success probability is small, then you have to wait a long time for success, so that's when you have a larger mean. Okay? And let's actually find the extinction probability. Let's find pi, the extinction probability. Extinction probability. Okay? Alright, so we had a theorem for that in the previous video. It is going to be 1 if m is smaller or equal to 1, and it's going to be s naught in the interval 0, 1, being the fixed point of the generating function if m is larger than 1. Okay? So we are looking for the fixed point of the generating function for s naught between 0 and 1. Okay, actually, even in this case, even in the case m smaller or equal to 1, so when we have probability 1 extinction, even then the smaller fixed point, the smallest fixed point in the fixed point in the interval 0, 1 is the one we're looking for because it's equal to 1. So even in this case, it's always true actually that the extinction probability is the fixed point of the generating function on the interval 0, 1, closed interval 0, 1. Okay. Now, what is the generating function of this pessimistic geometric? We calculated this before. It's p over 1 minus qs. That's the generating function for pessimistic geometric. So what we want to do is solve this, find the fixed point of this function, find s naught, where p of s naught equals to s naught, or p over 1 minus q s naught equals s naught, or p equals s naught minus q s naught square, just by rearranging. Notice that in the interval 0, 1, 1 minus q s naught is never 0, so there is no problems with that. And let's just collect things on the left, for example. Q s naught square minus s naught plus p equals to 0. And then let's solve this. S naught will have two solutions. 1 plus minus square root of 1 minus 4qp over 2q. These are the two solutions, but they are not actually in very nice form yet. And to bring them into a nicer form, you can actually notice that 1 minus 4qp is nice. When you have these numbers q and p adding up to 1, then sometimes they can give you surprises. So let's use P, and let's use 1 minus P instead of Q. So what is that giving me? It gives me a 4P square from the P square. It gives me a minus 4P and the plus 1, and the good surprise here is that this is actually a full square. It's the full square of 2P minus 1. And that's good news, because if I plug that in, then I have 1 plus minus the square root of a full square, which gives me the absolute value of 2P minus 1 with a plus minus. Okay, now the absolute value is also a plus minus, except it looks into the sign of what's inside, but it's also a plus minus. So together with this plus minus, I really have two cases. Either it's 1 plus 2P minus 1, or it's 1 minus 2P minus 1. Okay, so it's either 1 plus 2P minus 1 over 2Q, which gives me P over Q, or it's 1 minus 2P minus 1 over 2Q, which is 2 minus 2P, which is twice 1 minus P, which is twice Q over 2Q, so the whole thing is 1. So either I have P over Q or I have 1. These are the two solutions. And now I need to split cases. So there are two cases, of course, according to the theorem, and these two cases will be reflected here. Either m is smaller than 1 or m is larger than 1. So let's split these cases. If Q is, so if Q is smaller than P, say smaller than or equal to P, what happens then? If Q is smaller than or equal to P, then notice that my expectation is Q over P, so M is Q over P, it's smaller than or equal to 1, and then out of these two, which are in the interval 0 or 1, so then what I can see is that P over Q, so my first root, P over Q is bigger than 1, okay, bigger than or equal or strictly bigger than 1, and 1 is 1. So my curve, my fixed point, is either at 1 or it's even outside the interval 0, 1. I definitely don't have any fixed point between 0 and 1. Okay, so my fixed point is at 1, and if P is larger than Q strictly, then it's the other fixed point is out of 1. So my curve actually goes out here and intersects the 45-degree line outside my interval. So that's the only fixed point I have, and I'm back into the extinction picture here. So then the answer is that probability of extinction is the fixed point on the interval 0, 1, it's 1. If on the other hand Q is strictly larger than P, which means that M is strictly smaller than 1, then P over Q is going to be less than 1, strictly less than 1. So in that case, I am going to have a true fixed point of interest inside the interval. Let's bring this a bit further up. I'm going to have a true fixed point somewhere here at P over Q and another one at 1. So then I'm really in the supercritical phase. I didn't tell you actually. M is larger than 1, of course, because M is Q over P, right? M is Q over P, so it's larger than 1, and that's called the supercritical phase, whereas M equals to 1 was critical, and m smaller than 1 is subcritical. Okay, and so then the fixed point I'm looking for is the one which is inside the interval 0, 1, and that's p over q. So the extinction probability is going to be p over q. With probability 1 minus that, the thing survives forever. With probability p over q, there is going to be a last amoeba and nothing thereafter, but with probability 1 minus that, the thing survives forever. Let me just elaborate on this a little bit more. So in this case, the probability of survival forever, people sometimes call this theta, and it's going to be a function of p. It's 1 minus the probability of extinction. Okay, so that's the probability that at every time there's going to be at least one amoeba, and that is 1 minus, in the supercritical case, p over q, which you can actually plot a little bit nicer. So q is 1 minus p, and then I add a 1 minus p here and another p there. So 1 minus 2p over 1 minus p. And actually I want to plot this, and one way of plotting this is factoring out a 2. I'm going to say it's 2 minus 2p, which is of course not true. So I have to subtract a 1 over 1 minus p, because 2 minus 1 is 1. Okay? And then I can say it's 2 minus 1 over 1 minus p, and that's something I can actually plot. Not very difficult to plot this. So the survivor probability as a function of p is the following. So this is the region where p is smaller than q, or that's equivalent to p being smaller than 1/2. So I have this function here, 2 minus 1 over 1 minus p, when p is smaller than 1/2. And how does that function look like? Well, this is like a reciprocal function, except I have to transform it a little bit. So it's a reciprocal function, flipped upside down, shifted by 1, also flipped left, right, and shifted by 1 horizontally, flipped left, right, flipped upside down, shifted up by 2. At p equals to 0, it gives me 2 minus 1, which is 1. P equals to 0, it gives me 1. At p equals to 1/2, 1 minus 1/2 is 1/2, reciprocal of that is 2, 2 minus 2 is 0, so at p equals to 1/2 is 0. And now if you follow through what happens with the reciprocal function, you can find yourself that it's this piece of the reciprocal function. It does something like this. This is the survivor probability when p is less than 1/2, when we are supercritical. When we are subcritical, then pi is 1, extinction probability is 1, so theta is 0. So this is the diagram for survival of this Galton-Watson process forever. And so when p is large, then the geometric is small, because very fast we're having a success. So the offspring distribution is small in distribution, and we have a sure extinction. As p goes lower, if the success probability of the pessimistic geometric is lower, the geometric random variable itself tends to be larger and larger. We have more and more offsprings, and then we have a positive probability of surviving forever. In particular, when p is very small, then the geometric is large, because it's very hard to get a success. We need a lot of trials. When the offspring distribution is large, there is a lot of offsprings, then the survival probability is quite close to 1. So that's why theta p is going up to 1. When we have a lot of offsprings, then it's very unlikely that there is an extinction event anywhere in time.